everyone, I'm Ann-Katrin and I'm representing Team Sweden, and I will be presenting problem number 10, the cup flyer. So the task is a lightweight cup flyer thrown horizontally with a high backspin rises initially against gravity. Consider a flyer with a center of mass that it shifted from its geometrical center. So I will show you quickly a live demonstration with how this should look like. Okay, not a very nice one in that case. But explain the flyer's trajectory and discuss the influence of the center of mass location and other relevant parameters on the maximum height and the stability. So first overview, at first I will give you a little basic explanation on what forces are acting on our flyer. Then I will come to some expectations from the theory and a little bit investigate the parameter, its sensitivity, to motivate our experimental setup, and later we come to the experimental results and the comparison. So the very basic explanation is a term found often in the literature, so-called minus force. So basically, if you have something flying forward with a higher backspin rotation, you get a velocity difference from the top of the flyer to the bottom. This actually leads to a pressure difference, can be calculated by Bernoulli using the Bernoulli assumptions. And if you integrate that pressure over difference over the geometry you're using, you basically get the acceleration, which is dependent on only the forward velocity, the backspin, and a constant k, which is the ratio between the average air density and the cup density, which is dependent on the mass and the geometry of the flyer. So a little for the basic explanation. This is a sample trajectory you have seen in a little bit more ugly version previously. So at first, if you throw it horizontally, the forces are pointing in that direction. With the Magnus force pointing directly upwards. This leads to the initial rise of the flyer. If the cup flyer rises and rises within its trajectory, then it's pointing backwards. That leads sometimes to the little loop you might have observed, and then the flyer is gliding down. So what happens now if you shift your center of mass? As you have seen it you get kind of the same trajectory, but it's a little bit wobbling, a little less stable, and a little less reproducible, the experiment. So what you have here is, if you have a rotation not around the geometrical center, but around the center of mass, which is shifted, like schematically shown here, you get from a local velocity, which is not dependent only on the position anymore, but also on the time. And this violates the steady flow condition we use to calculate the force. So just some clarification before we move further, and we should investigate the maximum height and the stability. So the maximum height, it's the height we measure and the error within it, and the stability we will consider as the error in the height we'll measure. So for the assumptions in the theory used, if we consider a flyer with the center perfectly in the center of the geometry, we consider a steady flow, an incompressible fluid along the streamline, and no friction due to viscous forces locally, not globally, so we can use the assumption posed by Bernoulli. And for the later experiments, we assume no outer influences except gravity and air drag. We consider a perfect cup flyer without any turbulences at the sides, and we consider only the movement in the exact plane, so no movement in the third dimension. So to clarify and justify the setup we've used, we investigated how sensitive is this problem to all the parameters I showed you in the basic explanation side. So we simply calculated the forces and put these simple ordinary differential equations in an ODE solver. This is the coordinate system we've used. And then we went through all the different parameters. So the task states we should throw the cup flyer horizontally. So building an automated setup with this, it's quite hard. We found out after a try and error. So if you simulate the trajectory, well, you can see here the around 1.5 meter and 1 meter scale. You can see that around 0 degree the trajectory doesn't vary a lot, also not the maximum height. So we consider that it's slightly sensitive to small angle variations and won't investigate that the parameter any further in the experiments. It looks a little bit different for the initial velocity. So the typically measured initial velocity of such a flyer, if we let it fly, is around 7 to 8 meters per second. So if you simulate the trajectory around that value, we see that it is that as well as the trajectory, as the maximum height and stability is very dependent on that parameter. So we will come to that later. The most critical parameter to actually control well an experiment is the initial velocity, because it depends on how strictly we wrap that rubber band around it. It's kind of hard to control. So if you vary in the simulation the initial rotational velocity around the typical value, you can see that it has a little influence on the basic trajectory, but not that much on the initial height. So yeah, we consider that as a negligible factor in the experiment. And last but not least, the lift coefficient K, as it is known in literature, which is just dependent on the mass and the geometry of the cylinder. We see that it is slightly dependent, but I mean, if you see that the Magnus acceleration is directly dependent on the lift coefficient K, you might think at the beginning, okay, if I just increase K, then this flyer will go higher and higher, as we want to achieve with that flyer, of course, a maximum height at the beginning. But that's intuitively surprisingly not the case, because what happens if I have a large initial Magnus acceleration is that the flyer just goes very quickly into that loop and not in height. So we kind of see a rising height towards lower lift coefficients with a maximum around, with typical other parameters around 0.0. Yes. So therefore, we considered, considering this parameter sensitivity variation, that it is sufficient that we let this flyer fly with our hands, just using a lot of different cups, rubber band and tape, and we used coins to vary the center of mass. We just taped in between, like you can see here, in between these cup flyers to vary just the center of mass and not other parameters by itself. And for the parameter control analysis, we used the simple program tracker, where you can just track things in videos and get all the parameters you want out of it. So for the results, here in the graph you can see we vary the off-axis position here in centimeter. So it basically we place the coin like this in the flyer and threw it with different initial velocities. And here's the maximum height with the corresponding arrows plotted. And what you can see, and the red line is in Y the theory and an X the fit. You can see that the maximum height is lower if I go more and more off-axis. That's because of the reason I explained previously, that we violate Bernoulli's condition of a steady flow around the cylinder, and therefore the force acting on the cylinder, lifting it upwards, actually gets lower and lower as the layer of constantly of steady flowing air around the cylinder gets less and less. Mm-hmm. And we varied also the lift coefficient by mostly varying the mass and also the geometry. And what you can see here is exactly the thing we predicted in the simulation. So for a low lift coefficient, where we achieve the maximum height, we actually, it's exactly like predicted in the theory, what we said. So we consider this, as well as the simulation, as well as the overall theory, to fit very well into experimental results. So for a quick summary, in this problem we gave a basic and sufficient explanation of the trajectory itself, and found a very good fitting basic theory for the case that we have a perfectly centered flyer. We proposed a sufficient setup and an analysis method to actually investigate all these important parameters we posed on. And we tested this with this setup and found results fitting very well into that theory. So I would like to thank you for your attention.
So hello everyone, I'm Flavien from the Italian team, and I will present our position for the problem number 10, the cup flyers. So first of all, I would like to thank the reporter for this very interesting and thorough presentation. I would just like to remind the jury the exact terms of the problem. So a lightweight cup flyer is thrown horizontally with a high backspin, and we observe that it can rise against gravity. What we are asked is to explain the flyer trajectory, and especially to discuss the influence of the location of the center of mass and on other parameters on the relevant aspects of the flight. So what we liked in the reporter presentation is that first of all we had a nice derivation of the Magnus force. You could just have taken it from a textbook, but you took the time to explain where it comes from. So we found that really interesting. Then this the analytical form of the Magnus force was used in mechanical simulations, which seems to agree quite quantitatively with your data, so this is always a good sign. You managed to determine with this simulation to predict what would be the most relevant experimental parameter, namely the initial rotational speed, and you managed to take into account the various geometrical parameters and masses and moment of inertia of the cups in a single geometrical parameter, which we call lift coefficient, which is a really good idea to be able to compare a whole set of data with many different cups in a single way. So this is a very good point. But we also have some points which we found were not so good. For example, in the slide where you present the mechanical problem, you had an equation of evolution for the rotational speed, which was not justified, and we would like to. This would be one of the things we would like to talk about. It was not clear whether the simulations you presented were made with a balanced flyer, or if you simulated also the whole mechanical solid also with like the inertial matrix, and if you managed to make simulations with an unbalanced flyer. For the experiments, maybe it comes from the fact that you used only this lift coefficient to compare all flyers, but we did not have any idea of all the various cups you used. Did you try with very small cup flyers, or with large cup flyers, for example with a flower pot, which has more or less the same shape, which is 10 times bigger? This is one of the things we tried to do, so that you can explore a larger range of lift parameters. And also on the experiments, it was not clear whether you were able to measure or control in any way this initial rotational speed, because you said it's the most relevant experimental parameter. I would like to know if you managed to control this. So for the topics of the discussion, ranked by order of importance, and these two would be for further discussion to expand a bit the terms of the subject. So I would like to know what types of cup you use, if you can show us a whole range of parameters explored. If you managed to, what did you do about the experimental control of the parameters, this initial rotational speed? How did you do you understand the interaction between the rubber band and the cup? It's very complicated, but it could be a good idea to see if you manage to have some simple understanding of it. And most importantly, I would like to have a theoretical justification of the equation of evolution for the rotational speed, and what could be its experimental effect. And we can probably compare at this point our experimental prediction, theoretical and experimental prediction. And if we still have some time, I would like to know what happens, for example, according to you, when you shift the center of mass, not off axis, up or right, but on the axis on the left side. This is a condition we explored, and it had an interesting experimental consequence. And again, if we still have some time, what could change if you, for example, you keep the center of mass in the center, but you change the principal axis of inertia of the cup flyer, for example, by putting one mass here and one mass here, so that the axis of inertia are like this. So this is the end of my presentation. We can start with the discussion.
Yeah,
just one quick remark, because you said that I declared the initial rotational speed as the most important parameter. It wasn't the initial rotational speed, it was the initial forward velocity speed.
Oh, sorry.
I can show the...
Sorry, I think I may have misunderstood.
Yeah, just switch to that. this is the initial.
Okay, it is clearly the most important parameter for the height, but for the shape of the trajectory, what we found was that, yeah, for example, the initial rotation does change the shape a lot, and especially does it make a loop or anything. But you're right. I misunderstood what you said. So maybe we can go back to the topics I proposed. Should be okay. So, what is the whole range of experimental parameters you explore? Did you use only this type of cup?
We tried, of course, a lot of other cups because there are just a lot of different cups available. But the thing which matters most is the density, the average density of this cup flyer. So the mass compared to its volume. And we tried a lot of variety, but we found that using such plastic cups which have a very low initial weight is just the best option, because then you are able to vary the center of mass here with just simple coins. Because I mean, if your setup becomes heavier and heavier, it's very difficult to vary the center of mass if you just place like small things in here. So we just considered that using these type of cups it's the best choice for this experiment.
Well, we investigated also with cups which were smaller, like plastic coffee cups, which were about 2 times smaller in size than this, and we found that it tended to be more easier to give it a large initial speed, because what we think is that the rubber band would not slip on the side of the cup as easily if it's smaller than if it's really
okay,
big.
But the point is that this discussion is not
your
side. But I mean, I see the point of why it might be good to investigate also other parameters.
Okay, so I guess now for the second question, to control, you managed to control reliably the initial speed given to the...
Yes, so I can just switch back and show you what I meant with that. So here. So basically what we did is, of course it's not very you can't like control it during experiment, but what you can do is you can approximately control it and just film a lot of videos and select the best ones corresponding to the parameters you want to process. For example, for the initial velocity is basically varied by how much you stretch the rubber thing, and if you can take the initial velocity out very well, and if you select the trajectories where the initial velocity was in a certain thrust range of what we've measured, then we counted this into our measurement. So
before the end of the discussion, quite quickly, could you go back to the slide where you write the mechanical model, and for the evolution of the rotational speed, this equation was written as derivative of the rotation equals something minus the square of this derivative. I would like to understand more about this, because we wrote a slightly different equation, but it shouldn't matter so much. I would also like to know the characteristic time of evolution of the rotational speed, because you say something that the rotation speed will decrease because of friction. Is it this characteristic time? Is it comparable with the characteristic time to reach this maximum height? And do you think it has an impact on the we write?
Yes.
Okay.
I mean, actually, I have some opinions on this. Yeah, here just to illustrate what happens, because actually this problem is very sensitive for the coefficients of friction. We took these coefficients of friction out of common literature, because there are a lot of literature just expecting this phenomenon.
Okay, so hello, my name is Mate. I'll be the reviewer on behalf of the Croatian team. The solution that you have just saw was the solution to the cup flyers problem. And to say something about the reporter. The reporter pointed out some important parameters that were important for... pointed out some important parameters. They made a clear and understandable presentation. I honestly liked it very much because it was very easy to follow. They went through the problem point by point. They had a good simulation of the problem and stated the limitations of their work. The remarks that we have is that they vary the center of mass only along the plane of trajectory. They made no description of rigid body mechanics, and they made no remarks on the stability of the flight. The good points of the opponent is that they pointed out the lack of parameters in the mechanics of the system, and they questioned the reporter's method. The problem that they had was they often compared their solution with the reporters, and it is in our opinion that an opponent shouldn't do that, but should emphasize the solution and try to make a better discussion in the direction that the reporter decided to go in. For further discussion, we would suggest that we discuss about the stability of the flight. How would you quantize it? And it doesn't just have to be the stability in the plane of the trajectory, but the stability maybe of the rotation perpendicular to the plane of trajectory, and alternative methods for consistent initial conditions. For instance, initial velocity and initial moment of inertia, and the flight trajectory when the mass is shifted off axis flight. We could discuss what would happen when you would put more coins on one side and on the other, and so on. So that would be all for the reviewer speech. We could continue discussion. Okay. So in the statement of the problem, it said to comment the stability. I was wondering what you would have to say about how did you define stability and how did you quantize it? Like how would you quantize the stability of a flight and find its dependence on relevant parameters?
I quantized the stability in one of my slides by the error in the height I was achieving.
Mm-hmm.
Because basically the stability of a flight is a measure of how sensitive it is to the initial parameters.
Okay.
So this is the main quantized measure for it I used.
Mm-hmm.
What we used also was as you mentioned, the stability on the plane of the trajectory, whether it stays in the initial plane we are launching the cup flyer into, or if it goes on one side or on the other side. And this is we saw that with a lot of cup flyers, it was really quite unstable on this plane. I mean, a slight experimental deviation at the start would cause the flyer to go to the right and to the left really easily and by a large margin.
But is it only the height that matters? Like
for the stability?
For the stability, yeah. Is this the only parameter that qualifies, that characterizes stability of a flight? For instance, if you're
yeah, sure.
If you were to have this, I suppose that this would be a more stable flight than this.
Yes,
so
of course.
Could you comment on that maybe? How would you measure it for starters, and how would you define the stability using these oscillations?
So the oscillations you like shown here, they come only from flaws in launching the flyer. So if you do the experiment, I don't know, 10 times or something, you will maybe have four. I mean, at least in our experiment, we will have four kind of not wobbling at all flyers. So we just took them into the account because it's very hard to model mathematically. Well, the initial flaws when launching the flyer, because it's like very dependent on how you exactly wrap the bend around it. So yeah, but I mean the height is one of the, I would say, best well measurable things.
Okay.
So we considered it to be a good question because I mean these wobblings, which are not intentionally induced by center of mass shifts in these directions, you also propose, and we can come back to that.
Yeah, okay.
To that. Other questions, but
yeah, I agree that the height is one numerical parameter which is really characteristic of the flight, and it's, as you said, it's really sensible to initial conditions. So if the flight is unstable for any reason, then it will have a large impact on the maximum height we can measure.
It is in my opinion that maybe I don't know how you measured and how you measured the velocity and initial moment of inertia. When you said that when you pushed out the cup flyer, it wobbled a bit and then stabilized after.
no, I didn't say that.
Oh.
I said in a lot of experiments it just happens just because it's very hard to launch. I mean, as you have seen in life, it's very hard to achieve a very good flight. So we just took the experiments for this evaluation of parameters which flew stable from the beginning on. Okay. Because of this wobbling influences a lot of
there is an error on my behalf. I was wondering what would happen if you were to put some coins on the axis of rotation. What would you think? What do you think would happen?
Well, in my team we did the experiment, and what we observed was quite interesting. If the center of mass is still on the axis but shifted on center, then it means that, let's say it's on the right side for the jury. We have the center of mass which is here, the lift which is still symmetrical on the center. It means that we have a moment exist on the cup which is oriented, say, towards me.
Mm-hmm.
If the angular momentum of the cup is like this, it means that for the angular momentum theorem, then the variation of this of the angular momentum of the cup is varies in this direction, and this is what we see actually. If we move the center of mass, then once we launch it, it precesses and it falls by turning a bit on this side and this.
Yeah,
This
I
is
would
the
say
principle.
that the things may enter the discussion.
Okay. Yeah. Does anybody have any questions?
Maybe to comment on that.
Yeah.
I mean, of course, we try to vary this because this is like also another off-axis position we try to do. But it's actually it's not that trivial with the cups we used for all these cups to ensure that the center of mass is only varied in one axis, but in this dimension, and not also on the other axis.
But if it's varied on the other axis, then it causes wobbling.
Yeah, of course, as well. But
And we observed that there is this precession without wobbling, so we were pretty sure about moving the center of mass.
I mean, of course, the intuitive solution to that is, I mean, we can like demonstrate on a Tarek tape.
A question for
Yeah, that
you.
would be
Would you
great.
characterize the precession as a certain parameter of flow?
What do you mean?
Would you characterize this precession as a certain parameter of the stability of the flight?
The off-axis
Yeah.
position.
Yes.
This rotation.
Yes, the moment on the cup is the proportional to the distance. If we move the center of mass by just the same mass every time, then the moment only depends on this distance
Mhm.
to where the lift is applied to where the weight is applied, and this is
Okay, sorry, do you have a question? Yeah.
Just a simple one. So you mentioned that it would be non-trivial to shift the center of mass along the length axis, but not.
Exactly.
But you are Australian team observer.
Are we not allowed to enter the discussion, sorry?
Yeah, you are not allowed.
Okay, then we have a question.
The shifting is along the axis. Wouldn't doesn't report think that we consider an unstable fact, and the opposite. Isn't that like an unstable fact that it just diverges to the sides and isn't?
If I manage by luck to not vary accidentally the center of mass location on the other axis, it would fly stable just by maybe. I mean, of course, now I varied both of them, but if you like would let that thing fly, it would like just diverge to the side. And I mean, of course, the forces are acting on it as well. But I mean, just because this cup flyer tilts, and if we take the integration of the geometry into our mind, the resulting force lifting it up would be lower. But if there's no like another shift, this flight would be also considered as stable because it would be technically very reproducible. But this was not our main discussion point, main point of investigation, because it's very, very hard to control in the experiment.
Okay, we have a question.
A question for the opponent. If you move
for the
coins-
reporter, you mean?
Yes, out of the axis, it will cause precession moving in a helicoidal trajectory. Helicoidal, sorry.
What was your question?
If you move the coins out of the axis, it will turn around.
Yes.
If you move helicoidal,
Helicoidal.
Helicoid.
Yeah, that could,
what do you think?
Yeah, this is what we observed. We were there.
But let's say, how would you? What do you think the? Let's say that you move the moment of inertia by stacking coins on the axis.
yes.
Is that okay? What
Yes,
would
I
you
mean,
say-
if it's perfect geometry and everything, yes, that would work.
Let's say, what would the radius of the helix be, the independence of the amount of coins?
I mean, if I put more coins on that, which is also varying the mass, this like also goes into the lift coefficient. So I think you vary two parameters at the same
Yeah,
time.
it's really
So
hard.
it's very hard to like give a very intuitive answer that if you don't know the other parameters of the
We have a question.
Does the opponent or the reporter have some better alternative method to get really consistent initial velocity, initial conditions? Like, I heard you were shooting like from rubber.
Yes.
Is there some alternative method maybe that would be able to reproduce initial conditions better?
I mean,
Either your opponent can answer.
I mean, you have to take into account that you have to achieve an initial velocity,
Yeah.
and you have to launch it also in forward direction.
Okay.
I mean, of course, a rubber band is maybe the most intuitive solution,
Yeah.
but it's very hard to like. I mean, what you can do is you can use a rubber band every time a new one, because I mean, rubber also like doesn't work that well after a few tries,
Okay.
and also like try to stretch it always in the same
Yeah.
amount. This is one possibility, but then you always have to consider that
Thank
might
you.
be something.
What are the independent, the minimal list of independent parameters?
The lift coefficient, if you take that as one parameter, the initial velocity and the initial rotation, because these are the three going into the calculation of forces. Taking into account that it's perfectly centered.
Okay, thank you. Next one.
About your simulation, did you at some point compare it quantitatively with one experimental trajectory? Well,
Yes, it was the first graph I've shown. This was like the points where the measurement in the line through it was actually the simulation where we...
And did you do that on all the trajectories, or is it consistent? The parameters that you fitted are consistent with the measurements?
It's consistent, of course. We compared like one kind of parameter variation, like the extreme ones, of course. But not for like everyone, just for some to see if it's consistent, like going on and on in the experiment. But yes.
Okay, any more questions?
Yeah.
Okay, you can start.
If it's okay. How do you determine where is the center of mass of your object?
The center of mass, I mean, of course we can like just, what we did to calculate it was just take a photo of this, and then by just taking, this is by taking into account that this is like perfectly taped together, then you can just calculate, because you know very well the mass of coins and the mass of the cup flyers. But it's also possible if you like, I can't show it now, but if you like stick into it and then see
what did you do?
What
you calculated from.
Yes, and also like if you either you can like just like try to balance it, and then you can see if it's perfectly balanced, or you can like stick a stick into that thing and just see like where it is. Yes.
Yeah, better.
I'm wondering about the stability part of the question, because you define the stability of flight as the variation in top height or maximum height. But then in answering one of the other questions, you say that when you launch this, it's very clear whether it's a stable flight or not. Sometimes it's wobbling and you just discard it. So it's the same wording, and I'm just wondering, is there an alternative definition of stability of flight which could be relevant for the problem?
Just let me clarify by saying this initial wobbling stability, this instability is just induced by launching the flyer, because it's kind of hard with your hands and stuff to control. This is the one type of stability I used, and the other type of stability is referred to how sensitive it is to the three main initial parameters I've used.
But what about the if the mass is right at the center in the launch and it's perfect launch, then the center of mass will be very well behaved.
Yes.
But if you displace the mass away from the geometric symmetry axis and you launch it perfectly, then what would you call that a stable flight?
It depends. I mean, stable if I launch it perfectly, yes, in terms of I launch it very stable.
So in that case, would the center of mass still describe a very nice line?
But I mean, yes, like the with a small error, of course, taking into account the error. I mean, there's not, in my definition of stability, there's no clear distinction between stable and unstable, but it's always like in between this error, I suggested.
Okay, Piotr.
Yeah. Can you provide us a recipe to calculate the maximal height, given that you have this type of the flyer without any center of mass displacement? So I give you the initial parameters, and are you able to parameterize the maximal height I will be able to achieve with
what initial parameters do you mean?
Look,
I mean,
Like
what
the
parameters?
focus-
Just the geometry?
I give you this cap,
Okay.
and I give you the forward velocity and initial rotation of the velocity. Are you able to parameterize the maximum height?
I can like simulate it, yes.
Yeah.
I mean, then it's only dependent on the angle if this is the only parameter which is left here.
Mhm.
So if I choose a like bigger initial launching, and then it will also fly higher, as I presented in the. But yes.
Okay, if there are no more questions, then let us applaud all the participants.